Okay. Welcome everyone and to the Wind Turbine Performance Workspace monthly meeting. And today we are very happy to have Eric Simley from Unreal to share with us some of the work he has been doing along the topic of turbine performance. And like we did in the previous months, and Eric probably going to go over his presentation in the first 30-35 minutes, and then we have about another 15-20 minutes to have an open discussion. And we have scheduled one more meeting in August, and we do have a speaker lined up for August, Katik Badrinath. I didn't see Katik here today, but she was ready to give a talk on August the 19th. And now we probably need to discuss also a little bit, is there enough interest for us to keep going to the fall semester, to the next 4 months of the remaining year? Okay, but before we get to that point, and Eric, and floor is yours, or the screen is yours, whichever suits you. Okay.
All right, thank you. I think I have to change some settings so I'm allowed to share my screen. Yeah, sorry, this could take just a second. I have to enable admin rights so I can change my settings. Okay, I'm really sorry. I'm gonna have to rejoin the meeting just so I can share my screen.
Well, no problem.
Yeah. All right, sorry about that. I usually use Teams to present, so I guess I hadn't enabled screen sharing on Zoom yet.
Okay, good.
All right, this works. Okay, great. So yeah, you can see the slides. Excellent. All right, so today I'll be talking about how to assess the change in energy for a wind plant from wind farm control experiments. And let's see, so I'm going to start just by talking about some wake steering wind farm control experiments that we've been involved in at NREL, and then talk about estimating the change in energy as a function of wind direction using what we call energy ratios, and then how we can compute energy ratios using software, open source software that we developed at NREL called Flask. And then the next step is to estimate the change in annual energy production. So I'll talk about that, and then also talk about an alternative method that was published by TNO in the Netherlands, and then just a slide on some other considerations when estimating the energy gain from from wind farm control. And yeah, also just a little bit about myself. So I've been at NREL for about 6 years now, mostly working on wind farm control and wake modeling applications. And then, yeah, before that, worked on mostly LiDAR assisted control and other wind turbine control applications. All right, so just I'll talk about a few wake steering wind farm control experiments. Just wanted to talk about wind farm control and wake steering in general a little bit before I started talking about the methods for assessing the energy impact of wind farm control. So I'm just showing one of the first wake steering experiment I was involved in at NREL, and maybe the second field experiment at a commercial wind farm that NREL participated in. So this was an experiment from 2018 to 2020. And it took place at a 5 turbine cluster that was part of a larger wind farm in the US. And it involved modifying 2 turbines T2 and T4. And they were modified to implement wake steering to benefit the power production of turbine T3, which was in between them. So when the wind was from the north, T2 was controlled. It had a yaw misalignment applied to steer its wake away from T3. And then when the wind was from the south, T4 was controlled to steer its wake away from T3. So for the north experiment, we used 2 reference turbines, T1 and T5. They acted as our power references that we compared the power production of the test turbines to. And then there was also a ground-based LiDAR that was used to measure the wind speed and direction. And when the wind was from the south, we also used T1 and T5 as our power references. And then for our wind direction and wind speed references, we used a combination of the nacelle measurements from T1 and T5 and then a SODAR. A little bit about this, the wake steering controller that was implemented. So this is specific to this experiment, but we use a very similar approach for the other experiments we've been involved in. Right, so the yaw offsets are applied to those turbines, T2 and T4, to deflect their wakes away from the downstream turbine, which was either 5 rotor diameters downstream from the north or only 3 rotor diameters away when the wind was from the south. And so we used a lookup table, which was the yaw offsets we would apply as a function of wind direction. And there was also a wind speed dependence. So generally, as the wind speed increases, then we reduce the yaw offset magnitudes to mostly mitigate the impact on structural loads on the turbine from operating with yaw misalignment. And we only used positive yaw offsets for this experiment because, if we had to choose between positive or negative yaw misalignments, then there's a slightly larger power gain predicted by models with positive offsets, and then it can reduce loads on the turbine blades when using positive yaw misalignments versus negative offsets. And then these offsets were optimized using NREL's open source Florus wind farm control and wake modeling tool. And then the offsets were simplified a little bit. So they had this nice linear ramp down from our maximum allowable offset of 20 degrees down to 0. And so I mentioned positive and negative offsets. We define a positive yaw offset as a counterclockwise rotation of the nacelle relative to the wind direction when viewing the turbine from above. So to implement this, we've participated in some experiments where we don't have access to the turbine controller. And then so we just have to add some extra hardware to modify the wind vane signal that's then sent to the turbine controller. Other experiments, we've worked with the OEM, which I'll talk about on the next slide or one of the next slides. And they're, we're able to just modify the turbine controller, and it's a lot simpler. But for these first couple experiments, what we had to do was add some external hardware, usually in the form of a National Instruments hardware, to intercept the wind vane signal and then subtract this yaw offset from it. And so I mentioned we use a lookup table approach as a function of wind direction and wind speed. And generally, these are just measurements from the turbine's nacelle and its yaw encoder. So we calculate the absolute wind direction, low pass filter that, and then take the nacelle wind speed measurement, low pass filter that. Those are inputs to our lookup table. We get the optimal or the target yaw offset in the lookup table for those wind conditions, and then subtract that from the wind vane signal, send that modified wind vane signal to the turbine's yaw controller, and then that will induce the turbine to yaw towards the direction we want to achieve that yaw offset. And then during these experiments, we've always toggled between baseline control, where we just send the original wind vane signal to the turbine, and wake steering control, where we send the modified signal to the turbine. We toggle every hour. Sometimes that's a little different, like 50 minutes, and there are reasons for that. But in general, it's been hourly toggling. So we have about half the data with baseline and half the data with wake steering control. We can use that to estimate the impact of wake steering on energy production. So then there was another experiment that we worked on. This took place in 2020, working with NG Green at one of their wind plants in France. This was part of the Smart Yield project. That was a French national project that we participated in. And so for this, we just had a single turbine that was modified to implement wake steering, called SMV6, and that was modified to deflect its wake away from SMV5, which was about 3.5, 4 rotor diameters downstream. And again, basically the same control strategy I showed on the previous slide, also with hourly toggling. And I'll be using results from this experiment for a lot of the examples in the rest of the talk, mostly because NG Green actually made the data publicly available from this experiment. So this data, 1-minute samples of this data set are on Zenodo, and they're also used as the example data in our Flask software. And then the last experiment I wanted to mention, because I'll show some examples for this as well, is the Awaken experiment, which is a big, stands for the American Wake Experiment. And it's been going on for a few years now, and it has about 1 year left. So this is taking place at the King Plains Wind Plant in northern Oklahoma. It's a collaboration with several national labs in the US, and then NG, who owns the wind plant, the King Plains Wind Plant, and GE, who manufactured the turbines at the wind plant. So for this experiment, we are working with GE. We're modifying the turbine software so we don't have to add this extra hardware to try to trick the controller into yawing. So there are 2 types of wind farm control that are being evaluated at this wind farm. One is called consensus control, and that's happening mostly on the west side of the wind farm. And I won't talk about this too much, but it's where the turbines are sharing information about their wind direction measurements with each other to try to improve the local wind direction estimates at each turbine and improve the yaw control. It's really implemented just as a spatial average of wind directions from neighboring turbines used as the wind direction for each turbine. And then on the east side of the wind plant, there are 15 turbines that are modified to implement consensus and wake steering control. And so there's a 12 turbine cluster with a pretty large turbine spacing in the north-south direction, which is also the most common wind directions at the site. Because these spacings were so large and it can be challenging to implement wake steering in a situation like that, we added 3 other turbines where there's a much closer spacing to the downstream turbine in the common wind directions from the south. So for those 3 turbines, the downstream turbine is 4 to 8 rotor diameters downstream. So we expect to see larger energy gains for those turbines. So anyways, I won't show any results from this experiment. We just started modifying the turbines to implement wind farm control in May, and we're really still in that initial phase where we're kind of working through the normal issues of starting a new control strategy. And so this will take place until June or July next year. So we should get about a full year of data from this experiment. All right, so next I'll talk about the methods used for estimating the impact of wind farm control on energy production. And this will focus on something called the energy ratio. So first I'll define some signals. Just using the turbines at the King Plains wind plant for the Awaken experiment as an example here, but we're going to define our reference wind turbines and then the test turbines. So the test turbines will be the turbines where we're interested in evaluating the change in energy production for those turbines with wind farm control. And then the reference turbines will be unmodified, so they're not implementing wind farm control, and they're also unwaked, so they're seeing ideally free stream inflow. So the reference wind direction and wind speed. So we're assuming that we don't have any other wind speed or wind direction measurements from met masts or remote sensing. So we just have to use turbine measurements to measure our inflow conditions. So for the reference wind direction and wind speed, we can just take the average wind direction and wind speed measured by a set of reference turbines. And then we also have the power production of the test turbines, and that will be the average power of the set of test turbines we're interested in, and same where we have a reference power, which can be the average power production of our reference turbines. And so the reference turbines, that will depend on what the wind direction is. We'll choose a set of unwaked turbines that are not affected by the wind farm control, by the wind farm controller. Let's see. I also want to mention that usually for this approach, since we're defining these signals as the average of our test turbines or reference turbines, we'll need to make sure that at each time step, we're including in the average, all the turbines, all of the reference turbines or test turbines are operating normally, so they're not curtailed or derated. And so we'll first filter to remove periods where any of the turbines are not operating normally. And so that can reduce the size of the data set that we're left with. All right, now to calculate the energy gain, we use what we call energy ratios, and I'll just define that on this slide. And so first what we do is we bin the data by wind speed and direction, and we could also bin further by other atmospheric variables like turbulence intensity. But typically we've just done wind speed and direction. And we often use one minute samples as just a nice balance between high frequency data, which has a lot of turbulent fluctuations and noise in it, and 10-minute samples, which could include too many different wind conditions. So we've kind of landed on this 1-minute sample, but that's by no means the optimal choice. For some situations, maybe we'd want 5 minutes or closer to 10 minutes. So we use a metric called the balanced energy ratio, and we'll calculate an energy ratio during times when we have baseline control, and then also when we have our controlled or wind farm control case. So for the energy ratio, we'll sum over, so first I should say we calculate the energy ratio for a given wind direction bin. So this way we can look at the energy gain versus wind direction. And within a given wind direction bin, we'll sum over all the wind speed bins, and then take the weighted average of the average power of our test turbines weighted by a wind speed dependent weighting factor on the numerator, and then we'll divide that by the same sum in the denominator of the average power of our reference turbines multiplied by the same weighting factor. And this weighting factor is just going to be the total number of samples in that wind speed bin, considering the combination of our baseline and control period data. So this is really just supposed to represent what the energy production of the test turbines is relative to the energy of the reference turbines. So kind of like a relative value of how much power, how much energy the turbines are producing relative to the free stream or unwaked turbines. And the reason we normalize by the energy of the reference turbines is we want to try to cancel out any other impacts that could be, or any other effects that could be impacting the energy of our test turbines. So maybe there's different atmospheric conditions, if there's high wind shear, or if we're not binning by turbulence intensity, if there's different turbulence intensities during our baseline and control periods. If we first normalize by the power of the reference turbines, hopefully that will kind of cancel out the impact. And so when we compare the energy ratios in baseline and control periods, we're really trying to isolate the impact of just the controller, the wind farm controller. So by dividing by the power of the reference turbines, we hope to cancel out those other confounding impacts. Okay, so then we have these energy ratios for the baseline and control periods. And then we can look at the change in energy with wind farm control just by looking at the difference between the energy ratios during wind farm control and baseline. Okay, so now some figures, which hopefully will make this more clear. So this is the example from that smart eel experiment I mentioned earlier. And this is showing on the left the energy ratios for the wind farm control periods in green, and then baseline in blue, as a function of wind direction for the sector where we have wake steering active. And that sector is indicated by the dashed lines that are showing the boundaries of where we're implementing wake steering. And I'm showing, in the solid lines, what we're measuring with the SCADA data. And then in the dashed and dotted lines, those are predictions from Florus, our wind farm control modeling tool, using some different assumptions on the bottom plot. So the top plot is just comparing the energy ratios for baseline and control cases. Bottom plot is looking at that difference between the energy ratios, showing what the gain is. And then also on these plots, showing the 95% confidence interval of the energy ratios. And that was estimated just by bootstrapping the data, randomly resampling which 1-minute periods we're looking at with replacement, And then we get this distribution, and we derive the confidence interval from that. So what this is showing is for wind directions about 205 to 225 degrees, there's an increase in the energy ratio when we have wake steering active, and that peaks at about 10% of the power of our reference turbines. And for this experiment, the reference turbines are circled in blue on the right, and it's just the average power of SMV 1, 2, 3, and 7. And we excluded SMV 4 from the set of reference turbines because it could be waked by our test turbines. All right, so yeah, also on this plot, you can see there are some wind directions where there's a loss in energy with wake steering. And so, we of course want to account for that when we determine what the total impact of wake steering is. And so that was for the downstream turbine where we expect to see an energy increase. And then now on the right, this is the upstream turbine where we expect to see a slight loss in energy because we're yawing the turbine, it's misaligned with the wind direction, so it'll generate less power. And so that's what we see here, a slight loss in energy at that turbine when wake steering is active. And then what we're really interested in is the sum of the power of the two turbines. So now we're looking at the energy ratio, considering the average power of the two turbines, upstream and downstream. And now the change in the energy ratio is significantly smaller, but we still see an increase in that energy ratio with wake steering for wind directions from 205 to 225. All right, so the last thing I'll talk about with these energy ratios is that we can not only find the change in energy during the experiment period, which is shown on the left, but we can also estimate what the long-term expected energy ratios would be, where instead of weighting the power in each wind speed bin by the number of samples collected during the experiment, we can weight them by the long-term windrose frequencies. And so this is an example of the windrose for this site from reanalysis data. And so that the long-term corrected energy ratios are on the plot on the right. For this experiment, we quantified the total change in energy with wake steering as how much it reduced the wake losses for this wind direction sector. During the experiment, we estimated that wake steering reduced the wake losses by 5.7%, and the confidence interval of that estimate was very large, even overlapped with 0. So there's a lot of uncertainty in this estimate. And then on the right, for the long-term corrected energy ratios, the wake loss reduction was estimated to be significantly higher, close to 10%. And again, there's a large 95% confidence interval on that estimate. All right, so next I wanted to go through how we can calculate these energy ratios using our Flask software at NREL. So Flask stands for Flores-Based Analysis for SCADA Data. And it's open source software on GitHub, and it's used for analyzing the wake interactions and wake losses in wind plants using SCADA data, comparing those wake losses to model predictions from Flores, and then evaluating wind farm control performance using SCADA data and comparing that to Flores. There are examples that are included with this software, and some examples use artificial data generated by Flores, and some use data from the SmartNeil experiment I've been talking about. So Flores is our steady state wake and wind farm control modeling tool, also available on GitHub, and that's just uses simple wake models like the Gaussian wake model and several other variations of that. And we use it to estimate the impact of wake steering on energy production for wind plants and to optimize wind farm controllers. All right, so the first step when we're using Flask to estimate the change in energy from a wind farm control experiment is to apply power curve filtering. So like I said, we want to remove periods when turbines are operating abnormally, when they're curtailed or derated or otherwise not producing their normal power production. So there are functions in Flask where we can use the wind speed, power, and turbine status if it's available for each turbine, and identify periods when the turbine is operating normally, when its power curve, or when its power is generally close to its normal power curve. So there are a lot of different filters we can apply for, stuck sensor filters. So if there's a wind speed or power measurement that's just remaining the same for several periods in a row, it will flag that. We can use the turbine status signal if it's available, and then apply some outlier removal power curve filtering. So for this example, we ended up with about 75% of the data that was where the turbine was operating normally for this turbine. Next, we apply northing calibration. So the wind direction signals the nacelle orientation at all the turbines is not necessarily calibrated to true north. So probably every wind plant I've looked at, there's some calibration that needs to be applied to the nacelle position so that they're referenced to north. And so we can use them to measure the absolute wind direction for our experiment to determine what the inflow conditions are. So to do this northern calibration, we'll take one of the turbines that's waked and calculate its energy ratio for all wind directions. And so that's going to show where the energy is, or where the wake losses are. So on this top plot, you can see from our measured data, we see these peaks and troughs where the turbine is operating in free stream conditions or where it's waked. And then we compare that energy ratio function as a function of wind direction to the predicted energy ratios using the Flores modeling tool. And then we can see if there's an offset between them. So in this case, the uncorrected energy ratios from SCADA are kind of a shifted version of the Flores predictions. So this suggests that the wind direction measured at that turbine is not calibrated to true north. So it has some offset in it. So then we can add different offsets to that wind direction, recalculate the energy ratios, then calculate how the correlation between that signal and the Flores predicted signal, and then just keep applying offsets and find where the correlation is maximized. And then that will tell us what offset we need to apply to the nacelle position to calibrate it to true north. So in blue here is the energy ratios that with an offset applied where we have the highest correlation with the Flores predicted energy ratios. So we can do this for each turbine or just the turbines we're interested in, and then have wind directions that we feel are calibrated to true north and we can use in the rest of the analysis. And so we can calculate the energy ratios for any combination of turbines. Even if we're not doing a wind farm control experiment, we might want to use those energy ratios to help tune a wake model. So this is an example where the energy ratio as a function of wind direction is used to tune the parameters of different wake models in Flores. And then for wind farm control, I showed plots similar to this earlier, but we can compare the energy ratios as a function of wind direction during the baseline and controlled periods. So this plot on the top is showing the energy ratios for the combined power production of our upstream and downstream turbines during baseline and wind farm control periods. This function in Flask also shows how many points or how many samples there are in each wind direction bin. And then it breaks that down into how many samples per wind speed and direction bin on the bottom row. So we can see there aren't many samples on the left side of this plot around 180 degrees. And consequently, we have higher uncertainty in our energy ratios for those directions. And then similarly, we can look at the change in energy or the uplift from wind farm control just by subtracting those, or looking at the percent change in the energy ratios with wake steering and baseline control. And we can also compare that to the predicted increase in energy from our Flores model, shown in blue here. All right, so now that we've talked about how to show these energy ratios as a function of wind direction, which is a nice way to visualize the impact of wind farm control and energy, we might really be interested in just knowing what that overall change in annual energy production is with wind farm control. So here we're using just something called the power ratio. And we're also binning the data by wind speed and direction and possibly other variables like TI. And then for each wind condition bin, so for each combination of wind speed and direction, we'll find the power ratio, which is just the average power of the test turbines over the average power of the reference turbines for baseline and control time periods. And then we can look at the change in the power ratio for a given wind condition bin. Then if we want to know what the percent change in annual energy production is with wind farm control, then yeah, we can come up with this equation to calculate that percent change. And in the numerator, we're summing over all of our wind condition bins, combinations of wind speed and direction, and looking at that change in the power ratio multiplied by the frequency of occurrence of that wind condition bin, which could be from a long-term wind rose from the site, or could just be derived from the experimental data we've collected. And then multiply that by the average power of our reference turbines in that wind condition bin. And then the numerator is just going to be what our baseline AEP would be estimated to be. And that's where instead of summing the change in the power ratio, we're just summing the power ratio of the baseline turbine, of the test turbines during baseline control periods. So Flask also has a function for calculating this total change in energy production. And you can define what sector of wind directions we want to look at. In this example, we're summing from 195 degrees to 240 degrees. You can define the range of wind speeds to look at. So in this case, we're looking at all wind speeds above 4 meters per second when the turbines are operating. And so based on the SCADA data, this function is estimating that the energy production is increased by 0.45%. It also gives the confidence interval here, the P10 and P90 values. And then we can compare that to the estimated total change in energy from the Flores modeling tool, which was a little bit higher in this case. So just showing that our wake model is over predicting what the energy gain will be. Of course, there's uncertainties in the field data, and so we would not expect to achieve that full potential predicted by the wake models. All right, so getting close to the end of the talk here, just wanted to talk about an alternative method to estimating the AEP gain using what I'm calling the TNO method. So this is based on a report called Active Weight Control Validation Methodology from TNO in the Netherlands. And basically everything I've shown so far, we're looking at energy ratios or power ratios. So we're normalizing the power of our test turbines by the power of power or energy of unwaked reference turbines. But this TNO method considers the case where all the turbines in the wind farm are actively implementing wind farm control. So we wouldn't have any reference turbines that we can use as our reference power because they'd all be operating with yaw misalignment to steer their wakes. So here to look at the change in power for a given wind speed and direction bin, we just take the average power of the test turbines minus the average power of, or average power of the test turbines during the control periods minus the average power of the test turbines during baseline control periods. And then using that can come up with the percent change in AEP. And then they also, this method proposes a modification to this calculation that can account for turbines being curtailed or derated at any given time step. So using the power or energy ratio method that we have in Flask, that's going to require all of our test turbines and reference turbines to be operating normally at each time step to use them, because we're taking the average of those turbines at each time step. But this TNO method suggests a way where we don't have to remove time steps where turbines are operating abnormally, where a subset of the turbines are operating abnormally, because we're not going to take the average power of all of our test turbines at each time step. Instead, the method will sum over all of our test turbines and sum the average power production of each individual turbine. So yeah, take the average power of each individual turbine first, and then sum over all turbines. So this way we can still use data from each time step for a given turbine for the time periods when that turbine is operating normally, and we wouldn't have to worry about if other turbines are operating abnormally during those time periods. And so this also looks at if you have a turbine that's operating or that's not operating normally, say it's curtailed at a given time step, you would not only want to consider that turbine as operating abnormally, but you'd want to flag all the turbines that are downstream of it as well, because they would be affected by the wake of that turbine. So if it's shut down, then those downstream turbines are going to be seeing different power production. So we'd want to make sure we exclude those time steps for those downstream turbines as well. All right, so last slide, just some other considerations for estimating the energy production from wind farm control. So we're doing these toggling experiments where we toggle between baseline and wind farm control every hour roughly. We usually discard an initial period after a control mode change, maybe a 10-minute period. So this will account for the fact that it takes some time for the turbines to achieve their new yaw offset set points. So we don't want to be analyzing data where the turbines are transitioning from the control modes. And then also it takes time for the wakes to propagate through the wind plant. So if we change from wake steering to baseline control, it'll take time for the wakes to settle into their baseline conditions throughout the whole wind farm. One thing we do is some of the first experiments, we just toggle between baseline and wind farm control every hour. But what that does is the same hour each day, we end up with the same control mode. So we might have baseline control at midnight each day. And so that could create some potential biases if we're sampling the same hours each day in the same control mode, just because the atmospheric conditions can be heavily dependent on the time of day. So maybe we're sampling too many stable atmospheric conditions with baseline control, or something like that. And then if we don't have any reference turbines that are unmodified, say all the turbines are active in wind farm control, then we still need to use those turbines to measure the inflow conditions if we don't have met towers or remote sensing instruments available. But since all of our unwaked turbines could be active in wind farm control, they might be misaligning they might be misaligned with the wind to implement wake steering. If we're using their nacelle wind direction and wind speed measurements to measure the inflow, we will need to apply some calibration to correct for the effect of yaw misalignment on those nacelle instrument measurements. And then the last is something that, the community has just started talking about in the past year, is that when we're changing our control mode, baseline or wind farm control, that can alter the wind plant blockage, so the upstream blockage at the wind plant. And so by changing that blockage, that could affect the inflow to our reference turbines. So maybe depending on the control mode, we're changing how much power our reference turbines could produce by altering the wind plant blockage. So that could create some additional biases in how we're estimating the change in energy production. But that's really just starting to be explored in the community through simulations. So, all right, well, thanks for your attention. And hopefully it leaves a little bit of time for discussion.
Well, thank you very much, Eric. So we have about 10 minutes left in the meeting for some discussion. I wonder, Erica, are you still available past the hour, or you need to pretty much finish by your 8 o'clock?
Yeah, I could stay a few minutes over, probably not too long, unfortunately. Yeah, sorry,
yeah, sure, no problem. I understand.
Yeah.
I think some folks probably need to leave. We probably, just in case there's additional questions, we let folks to engage in the discussion. Probably no more than 10 more minutes after the hour.
Yeah, I think that works.
Okay. Any questions, comments from the audience? Well, let me start the set of questions. Erica, you mentioned a number of the studies. I'm wondering, are the data associated with those studies somewhat public available, or a subset of those are public available?
Yeah, for some of them, well, I guess just one of the experiments we have data available. So I showed these different experiments. These papers in wind energy science describe this campaign, but those data are not publicly available. Proprietary issues. For the SMART-EL experiment, yes, the data from this February to May period, 1-minute samples are available on Zenodo. And if you go to the Flask software, then there's functions for downloading that data from Zenodo. I don't have the link to Zenodo anywhere in the slides, but these data are available. Awaken, a lot of the LiDAR and other measurements are publicly available on a Department of Energy data portal. and we still don't know if any of the SCADA data if we'll be able to make those public. So yeah, for now, it's really just this smart eel experiment.
Okay, I think there's a question from Scott. Can you point me toward any work done to show how Flores can be used to correct the noise calibration of wind signals? How reliable this method is? Erica, do you have some response to that?
Yeah. So yeah, in the Flask software on GitHub, there's a sequence of example notebooks, Jupyter notebooks. And so they step through this process of power curve filtering and then applying this northern calibration using the Flores energy ratio predictions. And so, yeah, just going to the software and the examples for the smart eel data and the artificial Flores data, it will walk through that process. So there's a built-in function for performing this. And yeah, we feel that it's a pretty reliable method, but one way to really check how reliable it is would be to do this northern calibration for several different turbines and see how well the offsets agree with each other. Yeah, I guess.
Cheers, Eric. Yeah, yeah, that's answered my question. Thank you.
Okay, great. Yeah.
Iris? You're muted, Iris.
Hi there. Thank you very much. It was a very interesting presentation. I have a question regarding the different software you've discussed here. So the Flask and the Flores and how they interact with each other. So are they autonomous, or we need to run first Flores and the results for Flores will need to feed into Flask for the modeling?
Yeah. Yeah, good question. So I mean, so Flores is typically, it's most commonly just used by itself for modeling purposes, and then we use Flask when we want to look at field data. So Flask, I mean, it does require Flores to be installed, and some of the applications we don't need to run Flores. So if we just want to look at energy ratios from the SCADA data, then we don't need to worry about Flores. But if we want to do things like the northern calibration, then we have to use Flores. And the examples will, they have functions to run Flores to generate the power production for each wind direction and wind speed. So it shows you how to do that. I can't remember if, like, in general, if you would need to run Flores separately or if there are built-in functions in Flask to do that. But yeah, it would require both software packages.
And what about the other ecosystems that you have in NREL, like OpenOA? Will there be an interaction between that, or they're totally separate?
Yeah, right now they're separate. For a while, Flask was using some power curve filtering functions from OpenOA, but now I think they're just written in Flask, and they're slightly different. We do acknowledge there's a slight overlap between Flask and OpenOA, because OpenOA has a method for estimating total wake losses, and Flask has some functions like that. But really, Flask is designed for this detailed analysis of wake losses as a function of wind direction and comparing that to Flores, whereas OpenOA is just trying to estimate what the total wake losses are for the wind plant as a single value, like its long-term average wake losses. But yeah, right now there's no interaction between Flask and any other software packages at NREL besides Flores.
Okay, thank you.
Okay, Erica, I have a few more questions. One clarification question on your slides number 12. I think the same notation happened in the other slides. So you have the W sub j on both of the numerator and denominator. I suppose the one is associated with the test turbine, another is a reference turbine. So that W is going to be different depends on the number of samples associated with the different turbines. Is that right?
Yeah, so here so the W sub j, that's just the weight that's applied to each wind speed bin when we're calculating the energy ratio. And we do make sure that that weight is the same for the baseline and control energy ratios, and the same, we're using the same weight for the test and reference turbines. And so that's,
I'm
yeah,
sorry,
so
if it's the same, they cancel each other and then you don't have anything.
Yeah, you know, I think I did not write this correctly. So it should be summing, there should be a summation on the numerator and a summation on the denominator.
Oh, I see.
Otherwise, yeah, you're right. The way it's written,
Okay.
they would cancel out, so it's incorrect.
Right. Okay, so one of the issue, Erica, I'm not sure you were in the meeting previously. You know, one of the issue, especially in the early part of the year, has been quite extensively discussed is the wind speed correction, right? And in some of the study here, you still use the turbine's own measurement, which is from the nacelle anemometer, I suppose, and to measure the wind speed, which is already in the wake. And my reading, you know, I could be wrong. In your study, because you have multiple turbines, you use some of the reference turbine to provide a reference wind speed. And is that the mechanism you try to, even the wind speed measurement is not exactly the free stream, even they are in the first front row. But as long as they are in a consistent bias state, they can be used as a kind of reference calibration for the other turbine. Is that how you handle this issue, or you just assume that we separate that issue of the wind speed correction versus how you're going to use the biased wind speed for the subsequent analysis? I'm not sure. It's a very long question. Did I get my point there across?
Yeah, I think so. I'll talk about that and feel free to jump in. But yeah, so when we're using the turbine's wind speed measurements or wind direction measurements, we're always using the unwaked turbines as our references for our reference inflow. But still, you're right that might not be the actual free stream inflow because of the, you know, nacelle transfer function, the yeah, all those effects. So yeah, just because the turbine's measuring 10 meters per second, maybe the true free stream wind speed is 11 meters per second, or I mean, that's an extreme case, but yeah, we're not too concerned about that because we still have a consistent wind speed measurement between our baseline and control periods. So we can use that for binning the data and comparing the energy production of the wind plant in the same wind speed bin for baseline and control periods, while acknowledging that might not be the actual free stream wind speed. At least it's a consistent reference. And then where it could be a concern is if we're using the windrows, you know, the long-term windrows frequencies to apply these weights to estimate AEP, then we would want to try to correct the wind speeds measured by those turbines so they represent free stream conditions. So maybe applying some nacelle transfer function to them. So yeah, I hope that partially answered your question, but
that's right. Yeah, I just want to clarify the thought process. On the very next slide, on slide number 13, actually, not on the 13, it's probably on one of the latest slide. I do, you know, the similar on this map, I do see there's a kind of LiDAR sonar here, right? There's a sonar somewhere close to SMV6. why not using that kind of speed measurement from those remote sensing to provide more kind of unweighted measurement? It's because they don't have a data.
Yeah.
Any other reason?
Yeah. For this case, the SODAR was not there during the control experiment, so it was collecting data maybe the year before.
I see.
So that wasn't available. There's also a wind cube between turbines 2 and 3 that's shown on the top there. That was available, but we found that its measurements were affected by the wakes of our test turbines. So we just weren't getting reliable measurements from that.
I see. So you also mentioned that the data being used is 1 minute. Is that just naturally to give you 1 minute? You actually test between 1 minute and 10 minutes. You find the use 1 minute produce more sensible results than using 10 minutes data.
Yeah, so we were for all these experiments, we start with 1 second data, and then we downsample that to 1 minute. And our reasoning is that we want to downsample that because just looking at 1 second data, there's a lot of noise there, a lot of just turbulent variations in the power and wind speeds at each turbine. So a 1 second wind direction, wind speed measurement from our reference turbines wouldn't really correlate with the power at the test turbine for that, that 1 second period. But if we use something more standard, like a 10-minute period, then the wind direction could be changing so much within that 10-minute period that it's really kind of averaging too many different conditions together. So we think that something around 1 minute, a 1 minute sample is a good compromise where it's really just measuring, a very narrow range of wind conditions when we're binning the data, but it is averaging some of that noise that we'd see in higher frequency data. But that really is an open research topic. I mean, maybe a different sampling period would be better.
Okay. Any question? Any more questions?
Excuse me, I have a question. I take a quick look to the Flash GitHub, and I saw the raw data. I guess it's for this experiment because it has like 7 turbines, and it has a merged data with the SCADA. That's 10 minutes, right? Am I wrong, or is that data for a different experiment?
So you're looking at the examples SmartEal folder?
Yeah. Let me just copy paste the link here. Yeah, that's actually the data I was taking a look. It has like 7 turbines, I guess.
So this is that's the examples artificial data, and I'm not too familiar with that, but so there's another folder called examples SmartEal, and that's where it uses the data from that experiment. Yeah, so I don't know if, I mean, it's artificial data, so I don't know if it's represents 10-minute period or what, but I can try to copy the SmartEal path.
So that's different with this one, right?
Yeah. So here is the example SmartEal, which
okay.
Yeah.
Thank you.
Notebook 2 is called download and format data set. So that will show how to download this data from Zenodo, and it's all 1 minute averages.
Okay, I appreciate it. Thank you.
Well, that's really great. Okay, I think we are almost 10 minutes past the hour, and any last comment, thoughts, short questions? Okay. Well, thank you very much, Erica, for the wonderful talk and all the resources you shared with us. And I will post the recording and the slides after the in the afternoon of today. And I look forward to see you all in another month.
Yeah, great. Thanks for the opportunity.